here, we say, okay, if the Hilbert symbol is 1, then it's matrix, that's fine. If the Hilbert symbol is negative 1, I only know they're not isomorphic to the matrix. Actually, all such cases, the corresponding quaternion algebra are isomorphic. So, all this with, maybe I'll write QP. All this with where the Hilbert symbol is negative 1 are isomorphic. And are division rings. Non-tuted though. So anyway, in terms of Hilbert symbol, will tell you whether, like, which quaternion algebra is up to isomorphism. It's only 2. Secondly, if we look at this Hilbert symbol, because this is really sort of telling you, in some sense, whether the quaternion algebra is matrix or not, or equivalent whether this quadratic equation has 0 solutions or non-zero solutions. So it depends only on, as we talked about yesterday, so that's why I kept it out. Take it down. So it just sort of map from the quotient of QP plus over the squares and 2 plus minus 1. This is first of all symmetric. This is easy to understand because the quaternion algebra dkAB is the same as quaternion algebra dkBA. Just swap the A, I, and J. And bilinear. To think of it as a kind of a pairing. It's a symmetric bilinear pattern. Bilinear meaning that, I'll write it over here.
Bi-multiplicative might be a better term.
What?
Bi-multiplicative might be a more intuitive term.
Bi-multiplicative, that's what you want?
Mm-hmm. Your lecture.
Are you allowed to pull out scalars?
Okay. According to Keith, this should be called bi-multiplicative. I try to Google the word. I'm not sure if you can find any result. So this, what this really means is that AB1, B2 is AB1, AB2. Okay, that's what I really mean. Yeah, perfect. And maybe I want to say that although we've been dealing with P's odd prime, so these two right now, they hold for P equals 2. In this case, it's not going to be, it's just Z-mod 2Z, it's rather sort of 3 complex Z-mod 2Z. Or you can think of it as a kind of a 2-dimensional vector space over F2, each one of them as a bilinear function on it. Explicitly. I'll give a formula in a minute, but then I like to be more intuitive, so I'll only give it in the case where it's odd. So give a table. Hopefully this will fit. What I want to put here is a Hilbert symbol. I want to look at the value at 1 gamma P gamma, 1 gamma P gamma. I really want to make a table and plot the values. And on the left table, I'm going to write 2 tables. So I have to separate out the case where P is common to 1 mod 4 or P is common to 3 mod 4. unfortunately. So let's see. Let's fill the table. So we know that if A and B, any of them is square, namely, for example, 1, then the corresponding quaternion algebra is a matrix. So therefore, I should put 1 here. And the rest we'll fill out later. What we're going to get is 1 for this one. If A and B are equal, they're 1, and the rest are negative 1. And when P is common 3 mod 4, it's a little bit different. Slightly different. They're all plus minus 1, so they all look the same. So again, the other one is also sort of 1 on this boundary here. It's actually sort of the same on the, so it's the same except the lower right, so 2 by 2 corner. P common to 1, P common to 3 are different. Over here is how you reverse it. Okay. So that's some sort of, instead of writing down the sort of 16 possibilities of the quaternion algebra. There are only really 2. Those minus 1s are all isomorphic. Okay. You can write it in terms of a formula as follows. A equals P to the algebra times U, and B equals P to the beta times V for alpha and beta integers, and UV is EP but not divided by P. Then the Hilbert symbol, that's a formula. It's minus 1 to the alpha beta to the P minus 1 over 2. This view, let me just write it down first. Where? You see a symbol that you join. You haven't seen before. Oh, actually, this is a little wrong circle. And this 1 if dot is a square in FP cross. It's a wrong symbol. Okay? This is a little bit of a fancy formula. Well, let's maybe check a little bit. So, for example, when P, today I'm just gonna talk about when P is common to 1 mod 4. In that case, P is common to 1 mod 4, so this is gonna be 2 times something, so the term will disappear. So what you're really getting at is some sort of Lagrange symbol, depending on whether U and V are the quadratic residuals or not. So you see that when alpha and beta are both 0, and then when A and B are units, so these two are automatically 1. So that's why you have 1 here, and you can sort of spell out the rest for a little bit. Let's somehow try to prove a little bit. I'm going to give a proof when P comes to 1 mod 4. In this case, a little bit easier. P comes to 3 mod 4, it's a little bit, takes more time. Okay? So, first of all, as I said earlier, D1 something or D something 1, they're matrices. So that explains the first row and the first column. Now I have to kind of go into the middle. What makes things easier is that when p is common to 1 about 4, minus 1 is a square. About p. Because FP cross is a single group of order p minus 1. That p minus 1 is divided by 4, so therefore minus 1 as a 2 torsion is automatically a square of something. So or rather it's a square, I mean, right, it's a square in Z mod PZ. And I managed to only cancel some ones in this case. Now, if minus 1 is a square in modulo P, then it is a square in ZP. And of course it's going to be a square in Q. So now I can take advantage of this. Remember that this quaternion was defined with variables, sorry, the parameter a and b is isomorphic to the same thing, where I mean a and b correspond to I and j. We have a third similar thing called k. The square of k was minus ab. So you can instead use ij, instead of using ij, we use I and k. So you get a and minus ab. They're all isomorphic. And now minus 1 is a square. So you can identify that with, just get rid of the square. So the square come in handy. Very. So I get rid of this p common picture. So now, so that if you have A equals B, this is going to be very easy because I can see you start with AB and you get A of the product. So now you have A and A, I get A and A squared. But this is a square, so it's a matrix. So it's visible as square. So that checks out these three circle ones. So I've checked out the first row for the column and then the diagonal. Now I have to handle the rest. And first of all, I want to show they're the same. I mean, first of all, like A and B is symmetric, so I just need to check these three. So what do I have? I have this one, for example. That's when A equals gamma and then B equals P. Right? And again, using that trivial isomorphism, I get to gamma and P gamma. So that's gamma and P, so that gets to this one. So this going here. And then on the other hand, I can swap P and gamma, that one. And then apply the product. So that's how it goes down here. So they're all isomorphic. The only last thing I have to show is that they're not matrices. And in fact, they're division rings, but due to time, I just want to show that. So we'll show that I think which one do I want? I want P gamma and not isomorphic. I mean, I can show their division rings. Just a little bit more time. Okay? So how do I do this? So therefore that really kind of separate out matrices from the other case. And show that the other case Hilbert symbol is negative. So by the proposition we proved, this is not isomorphic to a matrix if and only if that x squared minus gamma y whatever a and b should be p here. Anyways, change a little bit. Put p here. But they're all isomorphic. Only 0. proposition. This is the same as looking at a quadratic equation, saying this has only zero solution. So suppose this is not the case. So you have a non-zero solution. I can scale x, y, z by a large power p. So I can always assume that x, y, z are all in zp, and not all divisible by p. Otherwise, you can just multiply by p or divide by p to change things. Let's look at, and the next step I want to do it modulo p. But I want to do it modulo p so that I get nothing. So I want to make sure, for example, x is not divisible by p. So suppose now, if x were divisible by p, and if you look at the equation, so this is divisible by p, and this, of course, you have a p here. So that means that p must divide y. And now if p divide x and p divide y, these two are squares, right? You have p squared here. And this only has one p here. So that also implies that p must divide, p squared divide pz. So p divides z. So now they're all divisible by p. I can just divide by p at the beginning. You didn't have to kind of assume. We already assumed that they're all not all divisible by p. So that means that if you assume that x, y, z are primitive, sort of simplified as we have already here, then x is not divisible by p. So now I do modulo p. Oh, maybe I should say similarly. You can say that similarly this p does not divide y. Same argument. So now I can mod p. When I really modulo p, I see that x bar squared minus gamma of y bar squared bar equals to, where is it? Oh, this pz squared. That goes away. Mod p. This is in f. So what it tells us is this gamma bar is a square, actually. But we know that gamma bar is a generator of the second group. So it can't be a square. If it was a square, it can't be a generator. So. Okay. So that shows that these are not isomorphic to the matrix algebra, so therefore I put -1 in these boxes. And then go. At least when p is congruent to mod 4. And the other case, p is congruent to mod 4 is a little bit. You have to do more work. So, how much time do I have? How much time do I have? No time?
0 minutes.
Great. I talk about quaternions over Q next time.